To maximize the number of cars passing by this eye, we'll start off with a car that's 4 meters in length, followed by a gap that depends on the speed of the cars, and then we'll have the next car with its gap following. We want to express the number of cars that pass by this eye in terms of the speed. Let's see if we can use the example provided in the problem statement to generate a formula in terms of the speed. So in the problem statement, the speed of the car is 52 kilometers per hour. So we take 52 and divide by 15 kilometers per hour, and then it looks like we round up to 4 car lengths. We can express this rounding up with the ceiling function. We'll take the speed divided by 15 and take the ceiling of it. To calculate the length of the gap between any two cars, we take this ratio and multiply it by 4 meters. We'll let n be the number of these intervals consisting of a car plus the gap that follows it. The length of this car plus gap interval is going to be g plus 4, and we'll substitute for g. The ceiling of s over 15 times 4 plus 4, and we'll factor out the 4. Let's express everything in meters. So if our speed is s kilometers per hour, in meters that's going to be 1,000 s meters per hour. So the distance traveled by our cars in 1 hour is going to be 1,000 times s meters. So n, the number of the cars plus the gaps that follow them, we take the total distance traveled by the cars in that 1 hour and divide by the distance of a car with its following gap, and we'll substitute. And we'll cancel out the 4. I'd like to combine these s's, so let's see if we can get rid of this ceiling function. Let's say that s over 15 is between these consecutive integers p minus 1 and p, and we'll let epsilon be this distance from p to s over 15. So we can express the ceiling of s over 15 as the fraction plus epsilon. So now we can rewrite this expression algebraically in terms of the fraction s over 15. And let's see if we can combine terms to isolate the s variable. We'll do that by multiplying the numerator and denominator by 15 over s. We get 3750 in the numerator, and this is our denominator. And here we have n as a function of s. S appears in this smaller fraction in the denominator. If we want to maximize this fraction, we'd like to minimize the denominator. Let's see what happens as we increase s. As s gets very large, this denominator gets very large, and so the fraction approaches 0. Here again, as s approaches infinity, the number of cars that pass in front of the eye, when we rewrite it as this expression, we have this fraction in the denominator approaches 0. So this large fraction approaches 3,750, which means that n gets arbitrarily close to this number. Let's return to our diagram to count the number of cars. Again, here is our eye, and here is our first car, followed by its gap. Here's our second car, followed by its gap. This is the second car gap interval, and so on. Let's take n is equal to 3749.9. This is car and gap number 3749, and this is the 3749th car that will go past the eye. Our next interval will be 0.9 as long, so if this is the full gap, after 1 hour, we'll only get through 9/10 of this interval. But we will see the 3,750th car. So m, the maximum number of cars, is 3,750. The problem asks for the quotient when this number is divided by 10, and our answer is 375. If you'd like me to solve any other math contest problems, please leave them in the comments.